Hello, ladies and gentlemen. Today we're going to be going over key features of graphs. So everything that we're doing today you can do by just looking at a graph, and there's not really a lot of math to do. So first thing we're going to talk about are x and y intercepts. So intercepts are points where a graph intersects the x or y axis. An x-intercept occurs where y equals 0. And a y-intercept occurs where x equals 0. A function can have 0 plus, meaning 0 or more intercepts, but at most only one y-intercept. So in our example over to the right, these 2 points in red are the x-intercepts, and the blue point would be the y-intercept. So on number 1 in our examples, our x-intercept is right here, which is at 4, 0. Okay, our y-intercept is right here, is at 0, 2. On our next problem, we've got x-intercepts here, 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 and here. So our x-intercepts are negative 1, 0, 1, 0, 2, 0, and 3, 0. And our y-intercept is at 0, 6. On the next example, our x-intercepts are here and here, which are at negative 4, 0, and 2, 0. And our y-intercept is right here, is at 0, negative 2. So our critical points are where the graph changes its direction or shape. Extreme are points where the graph changes direction. The function has a minimum or maximum value, relative or absolute, at these points. A point of inflection is where the graph changes its shape but not its direction. So this is a maximum, this is a minimum, and this point in the center here where it looks like it has a little bump on it, but it really doesn't, is called a point of inflection. It's still a decreasing interval at that point, but it's just like a point of inflection. So relative and absolute extrema. So you've got relative maximum is a point with the greatest value compared to its points around it. So this is called a relative maximum. And the point with the greatest value over the entire domain of the function is an absolute maximum. And a point with the least value compared to the points around it is called a relative minimum. And then the point with the least value over the entire domain of the function is the absolute minimum. So notice in our diagrams over here that, let's look at some examples and then we'll go back to that. So with number 3 on our example here, we've got a minimum here. So that's a relative minimum. Okay, and I'm going to show you the difference between a relative and an absolute in just a minute. So our relative minimum is going to be negative 3, negative 5. That's our ordered pair for it. And our relative maximum is this point here, is roughly 0.33, 4.48. And the way I got those values is I plugged this function into Desmos, and I clicked on my critical points to get the relative minimum and maximum. So the difference between a relative minimum and maximum and an absolute minimum and maximum is, if you notice on this graph, our end behavior goes in opposite directions. One goes up and one goes down. Whereas this graph over here, they both go up. So this would be our absolute maximum, which is right there. And this would be, absolute minimum. And then this one's a relative minimum because it's just a minimum within that range, that short little span there. Whereas this point is the minimum for the entire thing. So that's why we call it the absolute. Okay. So on this one, we've got a maximum here, a minimum here, and then a point of inflection in the middle. Okay. So we'll start with our relative maximum. So our relative maximum is negative 1.34 and 5.9. Again, I got those numbers by plugging the function into Desmos. If you want to try that out, definitely try that out. Our relative minimum is 1.34, 0.10. And our point of inflection is 0.3. So, increasing and decreasing. So, anytime we're analyzing graphs, we go from left to right. So we want to always move from left to right when we're doing this because then we can see if the function's increasing or decreasing. So, for example, our increasing interval on this graph over here to the right, if we go from left to right, we are increasing on this red interval here, okay? From negative infinity all the way up to, looks like -2. -1, sorry. Then from -1, let me change colors here. So green, -1 over to 4 is a constant interval, meaning it doesn't go up or down, it just stays flat. And then last is from 4 to positive infinity, it is decreasing. So on the next graphs, we're going to be finding our increasing and decreasing intervals. So again, we're scanning from left to right for this. So at first here on this one, we're decreasing. Okay, so we're decreasing from negative infinity. So this is left to right. So from negative infinity all the way over to the left, all the way to +2 on the x, we are decreasing. Then, no, I'm sorry, that's at 0. Because that's on my x-axis, okay? Then from 0, let me change my color here. From 0 up to this point here, we are increasing. So that interval is going to be 0 and roughly 2.67. Then we are decreasing again from 2.67 to infinity. So next one, we start off decreasing from negative infinity to roughly -1.84. Then we're increasing from -1.84 to 0. Then from 0 to 1.09, we are decreasing. And then we are increasing from 1.09 to positive infinity. And next one, we start off increasing. So we are increasing, and we have a point of inflection here. Remember, points of inflection are considered not considered to be a change in direction. So we are increasing from negative infinity to negative 1.10. We are decreasing from negative 1.10 to 1.10. And then from 1.10, if I could write, that would be great. 1.10 to positive infinity, we are increasing for the rest of the function. So continuity is our next discussion we're going to have. So a graph is said to be continuous if there are no breaks or holes. In the graph. If there are breaks or holes in the graph, it is considered to be discontinuous. So we have three different types of discontinuity. If it's continuous, there is no different type. But if it's discontinuous, there's different types of discontinuity. First one is infinite. So this one is created by an asymptote. So if there is an asymptote, it has infinite discontinuity. If it's lined up, but it just jumps either up or down, that's called jump discontinuity. And then if it seems to be continuous, but there's just one point removed, it's called removable discontinuity. So number one is jump discontinuity. And that occurs at the line x equals 5. So this line here that I'm drawing in just a dotted line, that is our line where that jump discontinuity exists. Number two is continuous. And number three is infinite discontinuity. If I could spell, there we go. Okay, and that exists on the line of x equals 1. So this line here is where our discontinuity is. So last thing we're going to talk about is end behavior. So end behavior, I always go left to right with. So as x moves towards positive and negative infinity, end behavior describes what's happening to the value of the function, the height of the function. So we're going to describe the end behavior with the graph on the right. So I'm going to zoom in. So I'm going to rewrite, well, no, I'm not. So I like to go to negative infinity first. So as x, this is your x-axis, as x approaches negative infinity, so as we go to the left on this graph, the height of my graph is going up to positive infinity. So as x approaches negative infinity, the height of my graph was going to positive infinity. And as I go to positive infinity, or as I go to the right, okay, as I follow my graph to the right, it's going to negative infinity. So when we write out end behavior statements, we write the same thing every time, and we just fill in the blank. So we're going to write as x approaches, I like to start with negative infinity, as x approaches positive infinity, put a comma, and then f of x approaches blank. F of x approaches blank. Okay, so as we go to the left, my graph is going up to positive infinity. So we fill that blank in with positive infinity. As I go to the right, my graph is also going up to positive infinity. So we fill in the blank with positive infinity. Okay? So on number 8, we fill in our same stuff. As x approaches negative infinity, as x approaches positive infinity, f of x approaches blank. okay? So as we go to the left, my graph is going down to negative infinity. And as I go to the right, my graph is going down to negative infinity. So the next one's a little trickier. I'm going to write this one in blue. So as x approaches negative infinity, pretend that's an arrow. There we go. Approaches negative infinity. As x approaches positive infinity, f of x approaches blank. Okay. So as I follow my graph to the left, I'm going to change back to red. This is where it's going to the left. This is not going to the left. This is coming from the right-hand side down here. Okay. So that part is not what we're looking at. We're looking at my big red arrow. Okay. So as we're going to negative infinity on the x, as we're going to the left and following this graph, my graph is going down to negative infinity. Okay. And as I follow my graph to the right, so from left, so follow the cursor, from left to right, my graph is going up to positive infinity. Okay. So sometimes our graphs don't approach infinity. They approach a specific number. So the next graph, as x approaches positive, well, we'll start with negative infinity. I'm going to start with the second one. So as we go to the left, see how this one levels out? It doesn't go straight up or down. It levels out to a specific value. My end behavior for that is going to be f of x approaches -1 because it doesn't, that's the height that it's ending at, okay? And same way if I go out to the right, it's going to have a value of -1. So with our examples, as x approaches negative infinity, as x approaches positive infinity, f of x approaches blank. Okay, so 13 has a lot going on. I'm going to change colors to green. So as we go to the left, this is to the left on our graph, okay? So that's to the left on our graph. Our graph is flattening out to the value of about -2. So I'm going to fill in my blank here with -2 because it's flattening out to where the height is -2. And then when I go out to the right, it's also flattening out to about -2. Next one, as x approaches negative infinity, as x approaches positive infinity, f of x approaches blank. Okay. Let's change to blue. So as we go to the left, it's flattening out to about, let me see, I've got 0. So that's actually my x-axis that it's flattening out to right here. So I've got 0, okay? And then when we look in the right direction, it's doing the same thing. So they both flatten out to 0. So next one, as x approaches negative infinity, as x approaches positive infinity, f of x approaches blank. Okay, so as we go to the left on our graph, this one's going up to positive infinity. And as x goes to the right, we are approaching -5. So you should be able to complete the backside of the packet that you have. If you have any questions, let me know when I get back. Hope you have a great day. Bye.